where we are trying to understand discriminative model. When I say discriminative model, hello everyone, welcome back. So far in this course, we have looked at a lot of algorithms. So far in this course, we have looked at a lot of algorithms for supervised learning, specifically the problem of binary classification. And we said that last time we can look at two different ways of modeling a binary classification problem. So under supervised learning, we are looking at binary classification. And under binary classification, we said that there are two different broad ways of modeling binary classification problem. One is the generative model and the other is the discriminative model. And under the generative model, we have looked at several examples. Specifically, we looked at the example last time of the naive Bayes assumption, which assumed a class conditional independence, and then that gave us a naive Bayes algorithm that used the simple binary features. But then we said that we can also look at a case where we can think of real features, and that gave us a Gaussian naive Bayes, or sometimes also called as the Gaussian discriminant analysis. Both are just the same names for different names for the same algorithm. Whereas in the discriminative case, we have looked at some basic algorithms like the k nearest neighbors and decision trees, which are discriminative because we don't really model how the data itself is generated, but given the data point, what we are modeling is how can we get an answer for it, how can we make a prediction for it based on the data, right? So in some sense, you can think of this as there's a non-probabilistic version of a discriminative model where we are just we are trying to learn a mapping from input to output. So that is a discriminative model. What we are going to do is we are going to study more discriminative models from here on. And to motivate this, when we look at naive Bayes algorithm, for example, which was a generative model, which modeled p of y and p of x given y. But then at the end of the day, when we actually wanted to make a prediction, we would use p of y given x, and we use the Bayes rule. That's why the name naive Bayes. And the Bayes rule would tell us a relation between p of y given x and p of x given y and p of y, which we have already modeled. But what we saw interestingly in the naive Bayes case was that p of y given x was actually p of y given x greater than equal to 0.5, right? So that this surface can actually be written as a linear function of the input. So this is something that we saw. In other words, there is a line that separates the y equals 1 class from the y equals minus class in the best possible way. So then we can ask the question, well, we made a generative assumption, but then what ended up being the best possible classifier is actually a linear function. Why can't we directly model the classifier as a linear function in a discriminative sense, right? So which is what we are going to do today. What do I mean by that? Well, what we are going to do is the first thing is we are going to look at discriminative models for classification. Discriminative models for classification. where we are trying to understand discriminative model. When I say discriminative model, we want to model P of y given x, right? So we want to say how does the probability of y equals 1 given x looks like, and of course that will determine the probability of y equals 0 given x, which is just 1 minus probability of y equals 1 given x. So the question we ask is how to model P of y given x, right? So that is, you're given a feature. Now we want to be able to discriminate whether this feature is in class 1 or class 0. So we want to make some assumptions about this discriminating power, right? So what is the functional form of this discriminator? And the simplest assumption that we can make is that it's a linear function. What does that mean? That means the following. So simplest assumption, and yes, this is an assumption that we are making on how the data is generated. So this is where we are saying that the probability of y equals 1 given x, right? So this probability can only take two values. It can either be 1 or 0, right? So it's not really a probability. There is a deterministic thing that is happening here, but then trivially we can say that there is a probability of 1 or 0. But when will we say probability of y equals 1 given x is 1? Well, if w transpose x is greater than or equal to 0. Which means that let's say somehow somebody gave a feature x. We don't care about how the feature itself was generated because we're only modeling a discriminative model here. So somebody gives us a feature x. Now we have to decide the label y equals 1 or y equals 0, right? So to create, let's say I'm trying to create the training data. Remember, in the generative process of the naive Bayes, we put down a generative story that created the training data. Here also there is a story, but this is a discriminative story in the sense that we don't care about how the x is generated. We only care about how the y is generated given the x, right? So this is the discriminative story. And what is the discriminative story here? Well, if I am going to give you a data set, this is how I would give you a data set. I'll give you some arbitrary x, right? So there is no probabilistic model that is generating x that we are assuming. So I give you an x, but now when I have to decide what is the y corresponding to this x, what I'm going to do is I'm going to toss a coin, and this coin will have either both sides heads or both sides tails, right? So that's what it means to say that the coin has probability 1 or probability 0, right? So when will this coin have both sides heads? Well, when will this coin have probability 1? Well, when y equals 1, right? So which means that if for the given x, w transpose x is greater than or equal to 0, then I would simply say the label is 1. If for the given x, w transpose x is less than 0, then I'm simply going to say the label is 0. Equivalently, I mean, I can think of this as a probabilistic setup where the probability is just 1 if w of choosing y equals 1 if w transpose x is greater than or equal to 0, right? So the probability should not really confuse you. At the end of the day, it is equivalent to saying that simply I'm going to decide the label by checking whether x satisfies w transpose x greater than or equal to 0 or not in a deterministic fashion, right? So of course you don't know what the w is. I as a generator of this labels is going to give you the labels based on some w, right? So you as a learner, you do not know what the w is, but you know that there is some w based on which I'm giving you the data, which means what, right? So so this means that what we are essentially assuming about the data is that the data is linearly separable, or this is the linear separability assumption. So let's make that very clear now, right? So what does this mean? This means that let's say I have a data set, I see a data set like this, right? Where green corresponds to, let's say, label as 1, and red corresponds to, let's say, label as minus 1 or 0. Now if I see this data, right, so where green is red is 0 label, and green has label as 1, right? So y equals 1. This has y equals 0. Y equals 0. Now, I ask the question, can this data be generated according to the model that I've assumed? Well, if you look at stare at the data for a second, you'll realize that yes, this data is linearly separable, which means that I see this data now. Yes, this data could have come from this model that I'm assuming, where there is some unknown w, right? So maybe there should be some w, such that when the person who gave me the data labeled the data, that person used some w. I don't know what this w is, but I'm assuming that there is some w. In this case, yes, there is some w, right? So maybe this is the w which says that everybody on one side of w, the green ones are all on one side of w, the red ones are all on the other side of w, right? So for example, then I mean basically this example, we say that this example is allowed under our model. That is, we are putting down this model for the data's label generation process, and well, once you put down the model, then you ask what type of data sets are allowed, right? So this is a data set that is allowed under our model. Now let us also think about a data set which is not allowed under our model, right? So how would that data set look like? Well, you can again create very simple examples, right? So now here is a data set where you have lots of greens here, which corresponds to y equals 1, and let's say lots of reds here, which corresponds to y equals 0. Let's say there is a red here as well. Now I ask the question, well, could I have seen this data under the model that I'm assuming? Well, if I have seen this data under the model that I'm assuming, then somebody has given me the labels according to some w. Now, if you look at this example, there is no w such that all the points which have been labeled green are on one side of W, and all the points which have been labeled red are on the other side of W, right? So there is no such W. Earlier we said that there is this W, right? So this W, but then this W will not label this point correctly, right? So if the labeler had used this W, then the labeler would have actually labeled this point as green, not as red. But then I'm seeing this as red, so this W could not have been the W that the labeler could have used. Now it's not too hard to see that there could be no such W that could have generated this data, which means that we are saying under the situation that this data set is not allowed under our model. That is to say that, well, I'm assuming that I will never get such a data set, because your model should be able to, I mean, you can only work with data sets which the model can generate, and in this case we are saying that, well, this data set could not have been generated according to our model, so our model can never explain this data set, right? So now this means that there is no, I will never get such a data set, because that is to say that, well, I'm assuming that I will never get such a data set, because your model should be able to, I mean, you can only work with data sets which the model can generate, and in this case we are saying that, well, this data set could not have been generated according to our model, so our model can never explain this data set, right? So now this means that there is no linear separator that separates the greens from the reds in this data set, and so this model is not allowed in our data set. Now one can ask the question, well, this looks like a very simple data set which we should be able to allow in a reasonable model. I agree, right? So any reasonable model should be able to be able to allow the possibility of generating data sets like this, where you have these outliers also. Which is a disadvantage of this model, that it only allows linearly separable data sets. But what we're going to do now is, well, we are going to acknowledge that there is this disadvantage at this point, that we are only going to allow linearly separable data sets, and then ask the question, well, if I allow only linearly separable data sets, then how good can I do? Right? So can I develop algorithms which can do the best? If you cannot develop such an algorithm, then even in a simple case, right, so you have made such a strong assumption about the data set, about the model, even under this assumption, if you cannot develop good algorithms, then when these assumptions fail, when you have all these outliers and so on, then it's only going to be hard to develop algorithms, right? So the hope is that, well, we make the strongest assumption and then ask the question, can we develop good algorithms for this? And let's see then later on, once we have such algorithms, how you can play around with the algorithm to make it work for this slightly more complicated situations as well, right? So with that understanding, so let's say we make this assumption of linear separability, and now do the following, right? So I have this, and we want to find pairs which minimizes the 0-1 loss, right? So indicator of h of xi not equal, even if this h is linear. For a general data set, this is an NP-hard problem. We did say this, right? So this is NP-hard for a general data set. Even if for a general data set, this is an NP-hard problem. We did say this, right? So this is NP-hard for a general data set. Even if h is just linear functions, linear hypothesis, right? So which means that if I give you a general data set, which I'm not assuming comes from any model, if I give you a general data set of pairs of x comma y, and I ask you to find that line that makes the least number of mistakes, then that's an NP-hard problem. Even if you have to just find a line, it's still an NP-hard problem. It's a hard problem to solve, right? So what do we mean by a general data set? Well, there is no restriction on how the data set should be, right? So there could be outliers, there could be all sorts of mixing and matching between greens and reds that could happen, right? So in a general sense, if you want to find the best possible line, that's a hard problem. But now we are saying, well, I'm not going to allow all possible data sets. It's not a general data set that I'm going to deal with. Here is a data set which I'm saying has a very strong restriction that the data set is linearly separable. That is an assumption that I'm making, but of course I don't know which is the line that separates the data. I'm just seeing the data, but I know that there is some line that separates the data. Now the question is, under the situation, can I minimize this 0-1 loss, right? So that's the question that we are going to ask. Now, Now, how about with extra, linear separability assumption? What does that mean? That means that we have a bunch of data points which we know is linearly separable, right? So that is, there is some W such that sign of W transpose X matches the label Y. Now, under that situation, we know that the labeler is using some W to make these labels. Now, for that particular W, what do you think is this value? What is the minimum 0 1 loss? Pause and think about this. I'll tell you the answer now, right? So because the label, what do you think is this value? What is the minimum 0 1 loss? Pause and think about this. I'll tell you the answer now, right? So because the labeler is using a W to label +1 or 0. Now, if you had the W access to that W, then you will make 0 errors on the training set, because that W is what was used to give the labels. If I had access to that W, I'll make 0 training error, right? So the training error can be as small as 0 in this case, right? So you can get a linear hypothesis, which means a line which has 0 training error. Of course, I don't know which line this is, right? So that's hidden from me. The labeler has used some line, but I don't know which line it is. Now the question is it still NP hard to find that line, or are there algorithms which will help us find this line, right? So now, given that we have put such a strong restriction on the data set, now, well, we don't necessarily, we at least hope now that the problem is not too hard now, right? So it's only, that you're given a data set which has some line that separates the one from the zeros. Can you just find this line, right? So can you find a line that does this? It turns out the answer to this problem is yes, we can find such a line, right? So now what we're going to do is we are going to give a classic algorithm which actually tries to find such a line, right? So let me put down the algorithm and then we'll talk more about this algorithm. But before I do put down the algorithm, let me make this assumption very, very precise, right? So what is the linear probability assumption in more formally stated, so that there is no confusion about what we are talking about. It just says the following, right? So it just says that we are just assuming that there is some W, there exists some W in D dimension such that the sign of W transpose Xi equals Yi for all I in our data set, right? So this is the assumption that we are working with. Now we know that our data set satisfies this assumption. Can we find such a W, right? So this is the question that we are asking. Okay, so now let's go ahead and put down this simple algorithm, which is a very classical algorithm. So an assumption can we find such a W, right? So this is the question that we ask. Okay, so now let's go ahead and put down this simple algorithm, which is a very classical algorithm. The algorithm that we're going to see is called as the perceptron algorithm, and this was given by somebody called Rosenblatt in the 1950s. So it's called perceptron because Rosenblatt at that point was trying to understand how to recognize objects, right? So the vision problem, a computer vision problem, and he realized that more and more that decision making, the human brain makes decision based on these neurons and synapses and so on, and he got inspired by how a neuron fires, what makes a neuron fire, and he got inspiration from that, and then kind of built this algorithm that we're going to see now, which is called as the perceptron algorithm. So in fact, the history is that Rosenblatt went ahead and built a real purpose mechanical machine which implements exactly the algorithm. Solve the problem of vision. It can indeed can solve all reasonable decision making problems. With the power of hindsight, we know that the power of this algorithm and the way that Rosenblatt put it down and the way that we are going to look at now is restricted in the sense that it will work when the data set is linearly separable, and it may not work when it is not linearly separable, right? So we are going to talk more about properties of this algorithm in a little later, but before that, let's understand what this algorithm is, right? So what did Rosenblatt put down, and why is it that this algorithm is so important in understanding the basic ideas of classical machine learning? Okay, so let's begin, right? So what is the algorithm? Well, the algorithm's input is as usual our data set, which has x1 y1 ... xn yn, where xi's are all in Rd, and for the purpose of this algorithm, we are going to assume yi is either +1 or -1. Typically, we assume 1 or 0, but for the analysis of this algorithm, it's easier to assume 1 or -1. We could state the algorithm completely even if you assume 1 or 0, just that you need to be careful carrying around certain terms and so on, which we are trying to avoid here. in the simplest possible way to explain this algorithm is just assume that the labels are 1 and -1, right. So, but that does not restrict anything here, right. So, because it is just a label, at the end of the day you can think of the features as corresponding to emails and the labels as spam and non-spam. Here I am just saying that I am going to call the spam as 1 and non-spam as -1, right. So, that is not, that is just without loss of generality. Okay. So, what does the algorithm do? The algorithm is trying to find a W that correctly classifies all the data points if such a W exists. So, what it is going to do is it is going to do an iterative, it is an iterative algorithm. So, it is going to start with some W which is W naught, and this naught here indicates iteration number, right. So, this is which iteration of the algorithm we are in, and initially W naught is just 0. This is just a 0 vector, right. So, 0 0 0, this is just a 0 vector. It is a very simple algorithm. Let me put down the algorithm and then we will talk about properties of this. So, the algorithm goes as follows: until convergence, the algorithm is going to do something. What it is going to do is the following, right. So, pick xi comma yi pair from the data set. Right. So, if sign of W t transpose xi is not equals yi, well, is equal to yi, then do nothing, and we will talk about what the step means. Else Wt plus 1 equals Wt plus xi into yi, and that is it. This is the algorithm. This is the what is called as an update rule, and we will talk about this in detail. So, what is this algorithm? Well, this algorithm begins with initialization of W naught equals 0, and now it is going to see, you have a bunch of data points. It is going to find out if the current W naught is enough, right. So, if it classifies everybody correctly, if it classifies everybody correctly, then you are done. You have found a W that classifies all points in your data set correctly. If not, there is some point which your current W, whichever you are maintaining, makes a mistake on, right. So, which means that the sign of Wt transpose xi does not match yi, right. So, if there is such a point, then you update your W based on that point, right. So, using this update rule, which is Wt plus 1 is Wt plus xi yi. Now, remember, xi is in Rd, yi is plus or minus 1, depending on whether that point was labeled plus 1 or minus 1 in my data set. So, all you are doing is, you are maintaining a current W, you are looking at all the points in your data set. If you can find a point where the current W is going wrong, then you make an update to the current W based on the point where you have made a mistake. That is, you take the point xi yi where the current W Wt makes a mistake, and then just add xi into yi to your Wt to get your new W. And now, for this new W, you go through all the data points, see if it matches, if it predicts correctly all data points. If it does, then you are done. You have found a W that was current W Wt made a mistake. That is, you take the point xi yi where the current W Wt makes a mistake, and then just add xi into yi to your Wt to get your new W. And now, for this new W, you go through all the data points, see if it matches, if it predicts correctly all data points. If it does, then you are done. You have found a W that works, that has 0 error. Otherwise, you would have found a point where this W makes a mistake, and you will add that point in multiplied by its label to the current point, and you keep doing this. Now, what I am saying is that if you keep doing this, then I am claiming that you do this until convergence, right. So, that's a statement that needs some clarification, right. So, what do I mean by convergence here? Well, we will say that the algorithm has converged if you have found a W which correctly classifies all the data points, right. So, if not, you Welcome back. Makes a mistake on, right? So which means that the sign of Wt transpose Xi does not match Yi, right? So if there is such a point, then you update your W based on that point, right? So using this update rule, which is Wt plus 1 is Wt plus Xi Yi. Now remember, Xi is in Rd, Yi is plus or minus 1, depending on whether that point was labeled plus 1 or minus 1 in my data set. So all you are doing is, you are maintaining a current W, you are looking at all the points in your data set. If you can find a point where the current W is going wrong, then you make an update to the current W based on the point where you made a mistake. That is, you take the point Xi Yi where the current W Wt makes a mistake, and then just add Xi into Yi to your Wt to get your new W. And now for this new W, you go through all the data points, see if it matches, if it predicts correctly all data points. If it does, then you're done. You found a W that works, that has zero error. Otherwise, you would have found a point where this W makes a mistake, and you will add that point in multiplied by its label to the current point, and you keep doing this. Now, what I'm saying is that if you keep doing this, then I'm claiming that you do this until convergence, right? So that's a statement that needs some clarification, right? So what do I mean by convergence here? Well, we'll say that the algorithm has converged if you have found a W which correctly classifies all the data points, right? So if not, you are going to update this W based on the point where you make a mistake. If at some point you find a W where all the data points are correctly classified, then you're done, right? So it means that the algorithm is converged to that W. You don't need to make any more updates, and you just end the algorithm. Now the update rule is the only thing that is non-trivial happening here, right? So the only non-trivial step which is happening, which is a very simple step in this algorithm, is the update rule. It says that if you make a mistake, then add that point times its label to the current W. And we don't know at this point if this algorithm is going to converge, right? So because though I say until convergence, what is the guarantee that this algorithm is going to converge, right? So because I'm kind of adding a lot of things to my W and keeping on updating my W, what is the guarantee that I will actually find a W that eventually correctly classifies all the data points? Not clear at all at this point. So the moment I say until convergence, that needs to be backed up with an argument. So what we are going to do is we are going to understand whether this algorithm will actually converge or not, and to understand that we first need to look closely into this update rule, right? So because that's the only non-trivial thing happening in this algorithm. So we want to understand if the update rule is doing the most reasonable thing that we want it to do. Right, so that's the first thing that we are going to think about. So let's start understanding the update rule of the perceptron algorithm to see what it is trying to do. So the update rule of perceptron is as a very now there are two different ways you can make a mistake, right? So what are these two different ways your current WT can go wrong on a data point? Well, pause and think about this. It's nothing too hard to see. I'm going to say what these two types of mistakes. Mistake type 1 is when the algorithm predicts the label as 1, but then the actual label is -1, right? So which means that predicted, let's say predicted is 1, actual is -1. What do I mean by predicted is 1, actual is -1? Well, this just means that sign of WT transpose Xi is greater than or equal to 0, but Yi is -1. Right, so you have a current WT. You had a current WT and you find an Xi YI pair where it's making a mistake. Why is it making a mistake? Because with respect to WT, I'm predicting 1. When will I predict 1? When I see that Xi falls on one side of WT, right? So the positive side of WT or the non-negative side of WT, which means the sign of WT transpose Xi is greater than or equal to 0. But because it's a mistake, YI should have been -1. Right, so that's mistake type 1. Of course, mistake type 2 is just the symmetric opposite of this. Yeah, so here predicted is -1, but the actual is +1. Right, so why is the predicted -1? Because sign of WT transpose Xi was less than 0, but actual Yi is +1. Right, so the opposite condition happened. Both of these are mistakes, right? So but then the update rule is the same for both these mistakes. So we need to justify why both these mistakes, why the update rule makes sense in both these cases. Okay, so let's analyze mistake 1, right? So let's look at mistake type 1. Type 1 mistake is when I am predicting, the algorithm is predicting 1, but then the actual point label says -1, right? So you had a WT where this condition happened. WT transpose Xi is positive. Well, I should not say sign here, right? So it's just a sign is +1 or WT transpose Xi is greater than 0. Yeah, WT transpose Xi is greater than or equal to 0, but Yi is -1. 1, right. So now I updated wt plus 1 to wt plus xiy. This is my new w, right. So I'm believing that, well, the old w is no longer correct. Here is a new w which is correct. So now I should ask the question, well, I have updated my w to a new w, then how does this new w perform on the point where the old w was making a mistake? That's the natural thing to ask. Now, what do I mean by how does it perform on the point? How does it classify that point where the old w was making a mistake? Well, how can I find that? I need to look at the dot product of the new w. Well, I have updated my w to a new w, then how does this new w perform on the point where the old w was making a mistake? That's the natural thing to ask. Now, what do I mean by how does it perform on the point? How does it classify that point where the old w was making a mistake? Well, how can I find that? I need to look at the dot product of the new w with the same data point and see how that looks like, right? So, which means that I should look at w, okay, I should keep track of whether it is superscript or subscript, yeah. So, I should look at wt plus 1 transpose xi, but by definition that is just wt plus xi yi transpose xi, which is just wt transpose xi plus yi into xi transpose xi, which is norm xi squared, right. Well, this is what the new w's dot product with the point where the old w made a mistake, right. So, but now in mistake number 1, look at w making a mistake. So, I have updated my w to a new w, then how does this new w perform on the point where the old w was making a mistake? That's the natural thing to ask. Now, what do I mean by how does it perform on the point? How does it classify that point where the old w was making a mistake? Well, how can I find that? I need to look at the dot product of the new w with the same data point and see how that looks like, right. So, which means that I should look at w, okay, I should keep track of whether it is superscript or subscript, yeah. So, I should look at wt plus 1 transpose xi, but by definition that is just wt plus xi yi transpose xi, which is just wt transpose xi plus yi into xi transpose xi, which is norm xi squared, right. Yi into xi transpose xi, which is norm xi squared, right. Well, this is what the new w's dot product with the point where the old w made a mistake, right. So, but now in mistake number 1, type 1, this value is greater than or equal to 0. Norm of xi squared is always a positive quantity, right. So, this is going to be greater than or equal to 0. In fact, you can simply assume that the data points are all not all 0. So, this is going to be greater than 0, but because it's a mistake, this guy was minus 1, right. So, which means that this whole thing is negative, right. So, what does that mean? That means that earlier I was making a mistake because the previous w's dot product with xi was positive, whereas it should have been negative. Now, what do I mean? That means that earlier I was making a mistake because the previous w's dot product with xi was positive, whereas it should have been negative. Now, what I am saying is that the new w's dot product with xi is the previous w's dot product with xi minus something, right. So, you are subtracting out something from the old w's dot product. Well, the old w's was positive, so you are subtracting out something. That does not mean that the new w's dot product with xi immediately becomes, negative. We do not know that, but we know that it is moving in the right direction. Why? Because this is positive, it should have been negative, but it is positive. So, you are subtracting out something, so it is getting slower and lower, right. So, at this point it is going in the correct direction that the dot product should be negative, right. So, at this point we are not saying it is correcting the mistake, but the w is moving in such a way that the mistake, at least the dot product is going in the correct direction, right. So, that is what is happening here, and very similar thing will happen here as well, right. So, here also the second mistake type also wt plus 1 transpose xi is wt transpose xi plus yi into norm of xi squared, but now in this case, well, the first term is less than 0, whereas the second term is yi is plus 1 now, and so the second term is greater than 0. So, now also the new w's dot product with xi, you want it to be positive. The old w's dot product with xi was negative. What you're doing is you're adding a positive term to it, right. So, if it was initially negative, maybe minus 10, now I'm adding, let's say, plus 5, so it becomes minus 5. It's not yet, it's not yet positive, but then it's getting closer and closer to being positive, right. So, that's the idea. So, basically what is happening is, you can say that, the update rule is such that, now this argument says that the update rule is a reasonable rule, right. So, update rule pushes w in the right direction for xi, right. So, if the dot product is positive but then it should have been negative, then you are subtracting out something. If the dot product is negative but it should have been positive, you are adding something. So the update rule is kind of moving our W's in the correct direction. It does not mean that it is fixing the problem, but it is at least moving in the correct direction. Now this is a local discussion, right? So what we are saying is that, well, I made a mistake in some point xi, yi, and I am asking the question, how does the new updated W work for this xi, yi, right? So maybe you are lucky that the new xi, yi, it pushed in the right direction and it actually fixed the mistake of xi, yi also, right? So maybe the old W was making a negative dot product, whereas it should have been making a positive dot product. So you update the W, and good for you, the new updated W is making a positive dot product, which means that we have corrected the mistake for xi, yi. But that does not mean that the mistake that I corrected here for this xi, yi is not affecting some other data point in my data set which was earlier correct, but then because I made this change, has now become incorrect. The view, how does W's in the xi? True, positive, but then it is getting closer and closer to being positive, right? So that is the idea. So basically what is happening is, you can say that the update rule is such that, now this argument says that the update rule is a reasonable rule, right. So update rule pushes W in the right direction for xi, right. So if the dot product is positive but then it should have been negative, then you are subtracting out something. If the dot product is negative but it should have been positive, you are adding something. So the update rule is kind of moving our W's in the correct direction. It does not mean that it is fixing the problem, but it is at least moving in the correct direction. Now this is a local discussion, right. So what we are saying is that, well, I made a mistake in some point xi, yi, and I am asking the question, how does the new updated W work for this xi, yi, right. So maybe you are lucky that the new xi, yi, it pushed in the right direction and it actually fixed the mistake of xi, yi also, right. So maybe the old W was making a negative dot product, whereas it should have been making a positive dot product. So you update the W, and good for you, the new updated W is making a positive dot product, which means that we have corrected the mistake for xi, yi. But that doesn't mean that the mistake that I corrected here for this xi yi is not affecting some other data point in my data set which was earlier correct, but then because I made this change has now become incorrect, right? So another what I'm saying is that this local update, fixing it locally, it is not at all clear that fixing it locally will actually, is a good thing in the overall scheme of things, because fixing it locally might break something else for some other data point that could potentially happen, right? So can that really happen? Well, let's see an example to kind of understand this in action, right? So let's say here is our data set. So this is a simple example where I'm going to put some points here. Maybe there are some points like this, and yeah, maybe there are some points like this, and maybe there are some points like this. So this is my labeled data set that I have in my hand, and let's say currently I have a W like this. This is my, let's say, current W. Now, at some iteration I have this W, I have this labeled data set, and I ask the question, well, does this W make a mistake in my data set? Well, how do I check that? Well, I look at the line that this W corresponds to, which is this line, and now all the green points on the positive side and all the red points on the negative side? Well, almost, except one guy, right? So except this point here, everybody else is correct, right? So this is a point where I'm making a mistake. So which means that I need to update my W based on this point, right? So now how will that update happen? Well, greens are positive, reds are negative, right? So that's, let me make sure we write that. So this is +1. It's going to be the new W. Well, the new W is going to be, well, if this is X, the corresponding label for this in my data set is green, which is 1. So I'm going to, my new W is going to current W plus X into 1. I'm multiplying 1 because the label is 1, right? So this is, let's say, W, let me say this is W old. Now W new is just W old plus X times 1, right? So this 1 is just Y, right? So it's just a green point. So what does that mean, right? So this is my, so let me plot the X point now, which looks like this. This is the direction of X, which means that I'm going to add that to my old W, which, if I'm drawing it correctly, which we'll put it somewhere here, right? So this is going to be my W new, right? So this is W new, which is W old plus this X, right? So that's what it means to say I'm adding X. Okay, so now what has happened is my W has updated. So let me look at the new W, this is my new W, which is W new, and let's see how this W performs on my data set, right? So how would this W perform on my data set? This would say anybody on this side is positive, anybody on the below this orange line is negative. Well, if you look at the point X, now this new W is saying X is positive, which means that I fixed the problem for X. But have I fixed the general problem? Well, this has introduced new errors here, right? So these guys were earlier correct with respect to the blue line, right? So these were positive with respect to the blue line before for W old, but now W old has become W new, and so that the line has shifted, and because the line has shifted, these guys are all now mistakes, right? So I tried to fix the mistake of X for W old, and so I came to W new. I fixed the mistake of W old for X, but then this W new is good for X, but then it's bad for a lot of other guys, right? So which means that though the update rule is pushing correctly in the direction for the current point where you're making a mistake, it might introduce mistakes for other data points. So it's not at all clear if this update rule is actually a solid update rule, right? So, and that's one of the reasons why this algorithm is surprising and surprisingly effective also. So let's talk more about update rule. It might introduce correctly in the direction for the current point where you're making a mistake. It might introduce mistakes for other data points. So it's not at all clear if this update rule is actually a solid update rule, right? So, and that's one of the reasons why this algorithm is surprising and surprisingly effective also. So let's talk more about whether this is a good algorithm in the sense that this update rule, will it lead to a convergence, or you might keep fixing local mistakes but then introducing some other mistake somewhere else. Now if I fix that mistake, some other mistake will again get created, and this will keep on going on forever, that I'll never converge, right? So one might argue that. So if you're saying that the algorithm converges, then it means that we should say that this situation will never happen, right? So that we need to kind of argue, which is what we're going to do now, right? So but let me note down what is the problem that we saw here, and then we'll go ahead and try to fix this, right? So try to understand this better. Fixing W for 1x might affect decision for other data points. So need more careful argument for convergence. This argument is I mean, we have to be very careful when we are trying to argue convergence of this algorithm. Okay, so let's look at another example, which is another revealing example that will give us some insights into this working of this algorithm itself, which is in some sense a border case, right? So it's like a corner case kind of an example, but it will give us something useful. Let's say I'm going to plus 1, right? So this has minus 1, and I have a third point, let's say, which is somewhere here, which is minus 1.5 or half, and now this is labeled as minus 1, right? So this is a negatively labeled point. Now this is a positively labeled. This is my data set. This is plus 1, sorry. Yeah. Point is labeled minus 1. This is my data set, right? So first question that I would like to ask you is this a linearly separable data set? So just, I mean, this is a good thing to pause and think about, right? So with respect to our definition of linear separability, is this a linearly separable data set? In other words, what I'm asking is that, is there a W such that for the points labeled plus 1, W transpose X is greater than or equal to 0, and for points labeled minus 1, W transpose X is less than 0? If you can find such a W, then this is a linearly separable data set. If you cannot find any W, then this is not a linearly separable data set. So is this a linearly separable data set? Pause and think about it. I'll tell you the answer now, right? So just to make sure, so this is our data set, right? So 0, 1 half. Is there a W Xi is greater than and W transpose Xi is less than or equal to for all Yi, which is minus 1, right? So is there a W like this? Well, in fact, the answer to this question is yes, there is a W. What is the W? Well, that W is just, any W that is pointing along the positive x-axis. Now, if I take this W, let's say this is my W, right? So now, with respect to this W, my separator is just the y-axis, which means that for these 2 points, which lie on the y-axis, W transpose X is 0, which satisfies W transpose X is greater than or equal to 0, so the label has to be 1, which in fact is 1 in this case. And for the point which is on the other side of the y-axis, W transpose X is negative, and so the label is also minus 1. So this is a linearly separable data set according to the definition that we put down. So now what we want to ask is, so let's say I give perceptron this data set, just 3 points, and see what perceptron's algorithm does in the way that we have put down the algorithm, right? So it's instructive to go through this example so that we understand what's happening with this algorithm, right? So let me draw this again. So here is my data point, which is 0, minus 1 perceptron. How does perceptron work on this data set? It's going to start with W naught, which is just 0, 0, right? So this is a 2-dimensional vector. By our algorithm's initialization, it's going to be 0, 0. Now, what will it do? Well, what does 0, 0 mean? Well, so let's call this points x1, x2, and x3 so that we can keep referring to them easily. So W naught transpose x1 is 0, W naught transpose x2 is also 0, and W naught transpose x3 is also 0. Because W naught is 0, it's going to make a 0 dot product with everybody. So which means that for the W naught, my predicted y is y1 is plus 1, predicted y hat 2 is also plus 1, and predicted y hat 3 is also plus 1, right? So because the value 0, if it is greater than or equal to 0, my sign function is going to say the label is plus 1, right? So in this case, all 3 would be predicted plus 1. So which means I've gotten 2 points correctly out of 3, and the point where I make a mistake for this with respect to this be predicted plus 1, right? So because the value is 0, if it is greater than or equal to 0, my sign function is going to say the label is plus 1, right? So in this case, all 3 would be predicted plus 1. So which means I've gotten 2 points correctly out of 3, and the point where I make a mistake for this with respect to this W is x3, which is this point, right? So which means my W1 is just going to be W naught plus x3 into y3, because that's the point where I make a mistake in my data set, which is just 0, 0, which is my W naught, plus x3 is minus 1 half. And what is y3? Well, y3 is just, y3 in this case is the label of x3, which is minus 1. So that is minus 1. So my new W is going to be 1 times half. 1 times minus half, right? So which is, where is the new W? Well, my new W is going to be pointing in this direction, right? So this is 1 minus half. This is my W1, right? So which means that visually we can see that, so everybody on the below this diagonal orange line is going to be labeled plus 1, and above is going to be labeled minus 1. So now we ask the question, is this W correctly classifying all my data points? Well, almost, except that it is incorrectly classifying x1. x1 is a mistake. It's correctly classifying x2 because it's on below the diagonal orange line. It's correctly classifying x3 because it's above the diagonal orange line. But then x1 is above, but it's labeled plus 1, which is a mistake, right? So which means that now I'm going to update my W using x1, right? So which means my W2 is going to be W1 plus x1 by 1. Well, what is W1? 1 minus half, plus what is x1? x1 is 0, 1 times what is the label of x1, which is 1. Now what would this give me? Well, this is going to give me 1 plus 0, which is 1, minus half plus 1, which is half, right? So this is going to give me 1 half, right? So that's going to be my W2. Well, where is W2? Well, if you look at where W2 is, let me plot it using blue. Well, it's going to be half. Line is going to be diagonal blue line, right? So everybody on the right hand side of this diagonal blue line is positive, on the other side is negative, right? Again, you see that it is classifying x1 and x3 correctly now, but x2 is incorrectly classified. So which means that perceptron will make one more update, and it will, let us put that here, and with respect to x2, which means that x2 y2 has to be added. What's W2? W2 is 1 half plus x2 in this case is 0 minus 1. What is the label corresponding to x2, which is 1? So now the new updated thing would be 1 plus 0, 1 half plus minus 1, which is minus half. Well, W3 is 1 minus half, but we know this is also same as W1, right? So which was also 1 minus half. So what is happening now is that, well, we were at W0, which is 0, 0, from which we got W1, and we went to W2, and now again we are coming back to W1. Now we know that both W1 and W2 are not optimal for this data set, so that it makes one mistake each. But then what will happen is you will keep switching between W1 and W2, and the algorithm will never converge. So what does this tell us? This tells us that this tells us something interesting about the algorithm itself, right? So we started with a data set which for which according to our definition is linearly separable, and now we try to run our perceptron algorithm, right? So our goal was to see if perceptron algorithm will get us a W if the data set is linearly converged. If the data set is linearly separable, will the algorithm give us a W which correctly classifies all our data points? But now it looks like that's not the case, because we started with a data set which is linearly separable, though it had just 3 points, nevertheless it's still a data set. And according to our definition, it's linearly separable. But if I run the perceptron algorithm, it's not going to get me a W which correctly classifies all my data points. In fact, what would happen is perceptron algorithm will never converge. It will keep jumping between W1 and W2, and it will never converge, right? So that means that, you know, we cannot say that if your data set is linearly separable, then perceptron algorithm will converge, right? So that's not good enough, right? So that's the problem here. That's the problem that I'm going to kind of say here. No, but that's, so then one can ask, why did this happen, right? So why are we, though the data set is linearly separable, why did this algorithm fail to converge? Is it like, there is something about special about this data set which was carefully picked that made perceptron not converge, or in general perceptron itself is a bad algorithm, it will never converge, right? So we can ask that question, and if you think about that, right? So one of the properties of this data set is that we said that it's linearly separable, but in some sense, it's strictly linearly separable, right? So well, it's not strictly linearly separable, I should say. The reason I say that is that it's linearly separable, but then we are using the fact that there are points on the boundary, on the decision boundary, and for which W transpose X is 0, and fact that the reason I say that is that linear, right? So one of the properties of this data set is that which was carefully picked that made perceptron not converge, or in general perceptron itself is a bad algorithm, it will never converge, right? So we can ask the question, and if you think about that, right? So one of the properties of this data set is that we said that it's linearly separable, but in some sense, it's strictly linearly separable, right? So well, it's not strictly linearly separable, I should say. The reason I say that is that it's linearly separable, but then we are using the fact that there are points on the boundary, on the decision boundary, and for which W transpose X is 0, and we arbitrarily decided to say that W transpose X equals 0 means that the label is +1. That's because that's how we define the sign function, right? So, but then if the points are on the decision boundary, and it's a corner case in some sense, right? So because we can either be labeled as +1 or -1, but then we chose to do it as +1, and because of this arbitrariness of labeling points on the decision boundary, somehow that is affecting the convergence of perceptron algorithm. So then we can ask the question, well, if this is our definition of linear separability, then perceptron is not going to give us convergence always. So can I make a slightly more restriction on my data set and ask, well, if I assume something more than just linear separability, I will also assume that, with respect to that optimal W that actually classifies my positives and the negatives, no point should actually lie on the separator itself, right? So we can make such an assumption and then ask whether perceptron will converge or not, right? So what do I mean by that? So let's make our assumption that we want perceptron, that we want to assume where perceptron will work well more precise, right? So let's make that assumption precise. So here's the assumption. So to assume that we want perceptron, that we want to assume where perceptron will work well more precise, right? So let's make that assumption precise. So here's the assumption. This assumption is a very fundamental assumption, and it's called linear separability. Well, we are saying that the data set is going to be linearly separable. So it is linear separability, but then with a twist, right? So with gamma margin. Now this is the assumption that I'm going to make, right? So what does it mean to say linear separability with gamma margin? Well, it means in pictures it means the following, right? So you have a data set in 2 dimension again. Now again I'm labeling some points as positive, some points as negative. Let's say things like this, maybe like this. And now what is happening is, I have, this is a linearly separable data set, obviously, because I can draw a W like this, such that the line, this line separates the positives from the negatives. Maybe I'll remove this. So now it's not just linearly separable, it's also linearly separable with gamma margin. What does that mean? That means that if I can draw these lines which are parallel to the separator, I'm just going to adjust my point so that I can make my comment very clear. Maybe that's a point here, right? So now what we are saying is that you have a data set. Now this is the W for which this line is W transpose X equal to 0, right? So this is the set of all X such that W transpose X equal to 0. Now what we're saying is that there are no points that lie on this line in my data set. For there is a W which will separate my positives from the negatives such that there are no points that lie on the line. Which is one more way of saying that is to say that, well, I can look at these 2 lines which are parallel to the line that passes through the origin. This is the set of all X such that W transpose X equal to some gamma, maybe gamma is 5, which is 5 units away parallelly. I've moved my separator on the positive side, and this is the set of all X such that W transpose X equal to minus gamma. Now what does this assumption essentially mean? Well, it means that I will not get any point in the space between these 2 parallel lines, right? In other words, I'm saying that the data set is such that there is a W such that this W classifies the positives from the negatives correctly, and just not classifies it correctly, it classifies it with some gap, right? So some margin. So let me make this assumption precise, right? So we're going to say a data set which is just a bunch of x1, y1 till xn, yn as usual, is linearly separable with gamma margin if there is some W star in RD such that W star transpose xi, and the way I'm going to write this is into yi gamma. The gamma cannot be x and yn as usual. Set of all x such that W transpose is separable with this. This is the probability, but then with a twist, right. So with gamma margin. Now, this is the assumption that I am going to make, right. So, what does it mean to say linear separability with gamma margin? Well, it means in pictures, it means the following, right. So, you have a data set in 2 dimension again. Now, again I am labeling some points as positive, some points as negative, let us say things like this, maybe like this. And now what is happening is, I have, this is a linearly separable data set obviously, because I can draw a W like this such that the line, this line separates the positives from the negatives. Maybe I will remove this. So, now it is not just linearly separable, it is also linearly separable with gamma margin. What does that mean? That means that if I can draw these lines which are parallel to the separator, I am just going to adjust my point so that I can make my comment very clear. Maybe that is a point here, right. So, now what we are saying is that you have a data set. Now, this is the W for which this line is W transpose x equal to 0, right. So, this is the set of all x such that W transpose x equal to 0. Now, what we are saying is that there are no points that will lie on this line in my data set. For there is a W which will separate my positives from the negatives such that there are no points that lie on the line. Which is one more way of saying that is to say that, well, I can look at these 2 lines which are parallel to the line that passes through the origin. This is the set of all x such that W transpose x equal to some gamma, maybe gamma is 5, which is 5 units away parallelly. I have moved my separator on the positive side, and this is the set of all x such that W transpose x equal to minus gamma. Now, what does this assumption essentially mean? Well, it means that I will not get any point in the space between these 2 parallel lines, right. In other words, I am saying that the data set is such that there is a W such that this W classifies the positives from the negatives correctly, and just not classifies it correctly, it classifies it with some gap, right. So, some margin. So, let me make this assumption precise, right. So, we are going to say a data set which is just a bunch of x1, y1 till x and yn as usual, is assumption in some gap, right. So, some margin. So, let me make this assumption precise, right. So, we are going to say a data set which is just a bunch of x1, y1 till x and yn as usual, is linearly separable with gamma margin if there is some W star in R D such that W star transpose xi, and the way I am going to write this is into yi is greater than or equal to gamma for all I for some gamma which is greater than 0, right. So, this is the definition. So, it needs some parsing and we will do that now. So, basically what I am saying is that you are given a data set. Now, there is some W star, right. So, we are assuming that there exists a W star such that with respect to this W star, if I try to find W star transpose Xi and multiply it by Yi, then this product should be greater than or equal to some positive quantity, gamma. The gamma cannot be 0, right? So the gamma is a positive quantity. Think of this as 0.1, still okay. 5 is still okay. 100 is still okay, right? So it cannot be 0. It has to be some positive quantity, right? So what I'm saying is that there is a W star such that this W star has the property that W star transpose Xi into Yi is greater than or equal to some strictly positive quantity. Now, why am I doing this product W star transpose Xi into Yi? Well, this is a compact way of saying that if Yi is 1, then this is saying that for all the points which are labeled 1, W star transpose Xi is greater than or equal to gamma, which means that all the points which are labeled plus 1 have the property that, they are, sorry for that, they are on this side, right? Now, this side, when I say this side, it includes this, dotted line, right? So, the dotted line and everybody on the other side, right? So, this is the set where W star transpose Xi is greater than or equal to gamma, right? So, and now when I multiply by Y, right? So, which means that whenever Y is 1, it better be in this yellow shaded region. And whenever Y is minus 1, which means W star transpose Xi into minus 1 is greater than or equal to gamma. Equivalently, W star transpose Xi is less than or equal to minus gamma, which means that all the points which are labeled minus 1 in my data set must then have the property that, they are on this side of the, right? So, they are on this side. Of course, this also includes this line, W star transpose X equals minus gamma. Right. So, now this leaves this in between region, right. So, this region, there is no point in my data set in this region, right. So, this is the assumption that we are making, which means that in particular there is no point on the line W star transpose X equals 0. There is no point in my data set satisfies W star transpose X equal to 0. Now, I am not assuming anything about how big or small this gamma is, right. So, I am just assuming that there is some gamma which is positive. Gamma cannot be 0, which means that this gap could be as small as possible, but then we are saying that the gap cannot be 0. That means that no point can lie on the separating line itself, right. So, this is what we will call as linear separability, but then with this extra small mild condition that there should be a gamma margin. Now, which means that if we are making this assumption on our data, then, well, it means the previous, bad data set that we had, which just had 3 points, is disallowed, right. So, we are saying that we will not see such a data set in our data, right. So, this data set is not allowed under our model. Our model only assumes linear separability with gamma margin. However small gamma can be, it's going to have this assumption. So, this is assumption, right. So, this is the main assumption, and we are going to work with this assumption and see how this assumption can help us provide a proof of convergence for the perceptron algorithm, right. So, this is one of the first algorithm which had a, a proof for its convergence under this assumption, and so it makes sense to, go over this proof and understand, what are the important elements of proving this. And the reason why I want to do this proof in this course is because this proof will reveal something interesting about the dependence on the relevant quantities that make up a problem, which will lead us to more stronger algorithm. Proof in this course is because this proof will reveal proving this, and the reason why I want to do this proof in this course is because this proof will reveal something interesting about the dependence on the relevant quantities that make up a problem, which will lead us to more stronger algorithms later in this course, right. So, for that purpose, I will go ahead and do this proof just for us to get a sense for how can we argue that perceptron actually converges when we put down this small mild extra condition that linear separability with gamma margin. So, to prove this, we want to make two other small, very innocuous assumptions. So, this is assumption number 1, which is linear separability with gamma margin. We are going to make two more assumptions, but as you'll see, these are not really assumptions; they are just simplifications, so to say. The second one is what is called as the radius assumption. So, we can work without the second and the third assumption that I'm going to put down and still prove convergence, but it might make things easier and easier to work with if you make these assumptions, right. So, the math becomes slightly easier to analyze. I mean, otherwise you just have to carry on a few extra terms which we are trying to avoid. So, what is the radius assumption? The radius assumption says that for every point in my data set, the length of the Euclidean norm is at most some r, radius r, right. So, for some r greater than 0. Well, all this is saying is that you have a finite data set and all the data points fall within a ball of some radius r. This object r greater than 0. Well, all this is saying is that you have a finite data set and all the data points fall within a ball of some radius r. This is obviously true because if you have 100 data points, there is one data point which is going to have the highest length, and now if I put a Euclidean ball of radius equal to the length of that data point, then all the data points will fall within that ball, right? So for example, if I had a data set like this, maybe I have a bunch of points here, 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 maybe there are some red points here. Now I can look at the length of each point, and then I'll realize that in this particular example I've taken, this guy has the longest length. So which means that if I put a Euclidean ball of radius equal to this guy's length, of course I've not drawn the ball carefully, but yeah, so if this is r, then it means that all the points, the length of every point will be less than or equal to r, right? So by definition, because I've taken the largest point, so I'm just assuming that there is this r, right? So for any finite data set, this is going to be true, right? So this is what is called as a radius assumption, just that there is a big ball of radius r within which all my data points are, right? So this is assumption number 2. Well, more than assumption, it's a simplification. The third one is also a simplification, but it needs a slightly careful understanding. Without loss of generality, we can assume norm of W star is 1. Well, what is W star? Well, W star is this guy which separates my data set with margin gamma. Now I'm saying that W star's norm is actually 1. Now what does this even mean, right? So it means the following. So again, we have this data set. One is also a simplification, but it needs a simplification. The third one is also a simplification, but it needs a slightly careful understanding. Without loss of generality, we can assume norm of W star is 1. Well, what is W star? Well, W star is this guy which separates my data set with margin gamma. Now I'm saying that W star's norm is actually 1. Now what does this even mean, right? So it means the following. So again, we have this data set where let's say we have these positive points, and then there are these negative points here. And let's say we have a W which is like this, which separates the positives from the negatives using some gamma margin, which means that I have this, maybe I'll put a positive point here. Now this is a W, and this is the set of all x such that W transpose x equals gamma. Of course, this is the set of all x such that W transpose x equal to minus gamma, and all my data points are on both sides. But now I observe that this W's length is not 1, right? So maybe let's call this W star, right? So this W star's length is not 1, because the set of all W's whose length is 1 is, let's say, somewhere here, right? So maybe this is the set of all W's with length 1. Now what I'm saying is that, well, if you give me a W star such that it separates my data set linearly with some margin gamma. Now I can find another W star whose length is 1, which also separates my data set linearly. Maybe this is the set of all. So this W star's length is not 1, because the set of all w's whose length is 1 is, let's say, somewhere here, right? So maybe this is the set of all w's with length 1. Now what I'm saying is that, well, if you give me a w star such that it separates my data set linearly with some margin gamma, now this w is gamma. Of course, this is the set of all x such that w transpose x equal to minus gamma, and all my data points are on both sides. It needs my data point. It's called as a radius assumption, just that there is a big ball of radius r within which all my data points are, right? So this is assumption number 2. Well, more than assumption, it's a simplification. And without loss of generality, we can assume norm of w star is 1. Well, what is w star? Well, w star is this guy which separates my data set with margin gamma. Now I'm saying that w star's norm is actually 1. Now what does this even mean, right? So it means the following. So again, we have this data set where, let's say, we have these positive points, and then there are these negative points here. And let's say we have a w which is like this, which separates the positives from the negatives using some gamma margin, which means that, I have this, maybe I'll put a positive point here. Now this is a w, and this is the set of all x such that w transpose x equals gamma. Of course, this is the set of all x such that w transpose x equal to minus gamma. It's not 1, right? So maybe it's on both sides. But now I observe that this w's length is not 1, right? So maybe let's call this w star, right? So this w star's length is not 1, because the set of all w's whose length is 1 is, let's say, somewhere here, right? So maybe this is the set of all w's with length 1. Now what I'm saying is that, well, if you give me a w star such that it separates my data set linearly with some margin gamma, now I can find another w star whose length is 1, which also separates my data set linearly with some other gamma, which is still not negative, not 0, right? So where is that gamma? Well, I can pick that gamma, that w star, in the same direction, but then if I just normalize it to have length 1, now think of this as my new w star. Let's call this w star hat, maybe not hat, I'll just call this w star dash. Now what is w star dash? Well, with respect to this w star dash, well, with respect to the original w star, this line's equation was w star transpose x equal to gamma. Now if I do w star transpose x divided by norm w star on both sides, well, norm w star is a positive quantity, so that will not affect the equation. The equation still stays the same. But then what I can now do is, it's the same line, but now I can write this as w star by norm w star transpose x equal to gamma dash, where gamma dash is gamma by norm w star. So basically the gamma is rescaled. I got a new gamma dash, and now with respect to, now if I rename this w star by norm w star as w star dash, now this transpose x equal to gamma dash. Remember, it's the same line. I'm not changing the line. I'm changing the equation of the line by scaling on both sides. It is like saying that if y equals mx plus c is my original line, then so is 2y equals 2mx plus 2c, right? So I can multiply 2 on both sides. That doesn't change my line. It's still the same y equals mx plus c line, right? But now what I'm saying is that in this particular case, because I have divided by norm w star on both sides, the line is the same. But now with respect to this renaming, I can write the same line as the set of all x such that w star dash transpose x equal to gamma dash. It's a new w star. It's called w star dash, and the gamma has changed to gamma dash. It's the same line. Gamma dash is a positive quantity, because originally gamma was positive. I divided it by a positive quantity, still a positive quantity. But the advantage of doing this is that this new guy that I have now has norm 1. Which means that, if you give me a w star which separates my data set with some gamma, let's say gamma is 10, now I can create another w star by rescaling your w star to make sure it has length 1, and the gamma will rescale accordingly, right? So, but still, I now have a w star whose length is 1, which also linearly separates this data set with a different gamma. But because we did not make our assumption 1, just said that there is some w star with some gamma greater than 0, it did not tell me that gamma has to be at least this much or anything of that sort, right? So we allowed for any gamma greater than 0. Now we are still satisfying this assumption, right? So which means that without loss of generality, I can assume that w star, the length of my w, is actually 1, right? So because for every w star that linearly separates my data set with some gamma, there is an equivalent w star dash whose length is 1, which separates my data set linearly with some other gamma dash, right? So I can assume that the w star that is given to me is as well of length 1 itself, right? So this is without loss of generality. So now with these three assumptions, linear separability with gamma margin, which is the most important assumption, the radius assumption and the length assumption, we can now go ahead and try to analyze the proof of the perceptron algorithm, which we will do next. Okay, so let's analyze the perceptron algorithm with our assumptions that we have put down, right? So analysis. So what we are going to analyze is we are going to look at how many mistakes this algorithm makes, right? So the way we are going to prove that this algorithm actually converges is using the following method. We are going to say that the perceptron algorithm cannot make more than a certain number of mistakes. Maybe that number is 10,000, right? So we're saying that the algorithm cannot make more than 10,000 mistakes, which means that after it makes 10,000 mistakes, right? So it cannot make any more mistakes. What does it mean to say it doesn't make any more mistakes? It correctly classifies all my points in my data set, and so the algorithm would have converged. Which means that if I can get a finite number as a bound for the number of mistakes the algorithm makes, then that implies that the algorithm has actually converged, right? So which is what we're going to try and do now, right? So can we analyze the mistakes of this algorithm? How many mistakes will this algorithm make, right? So why do we care about mistakes? Because the algorithm only makes an update when a mistake happens, right? So now observe that an update in the perceptron algorithm happens only when a mistake happens. Okay, so now let's say we are at some point in running the perceptron algorithm. We are given some data set, we are running the perceptron algorithm, and let's say a mistake happens. Algorithm happens only when a mistake happens. Okay, so now let's say we are at some point in running the perceptron algorithm. We are given some data set, we are running the perceptron algorithm, and let's say at some point WL, or maybe I'll put the L above, WL is the current guess, and a mistake happens. So with respect to some data point x comma y, right? So I found a point where WL is incorrectly x comma y algorithm. Okay, so now let's say we are at some point in the running the perceptron algorithm. We are given some data set, we are running the perceptron algorithm, and let's say at some point WL, or maybe I'll put the L above, WL is the current guess, and a mistake happens. So with respect to some data point x comma y, right? So I found a point where WL is incorrectly classifying. So the moment I find a point where it incorrectly classifies, I'll update WL to WL plus 1 as WL plus x into y. This is my update rule. I know this, right? Now if you observe, what is happening is I'm adding a new point to my current old WL, right? So now what we're going to look at is we're going to ask how much is the length of my WL plus 1 growing, right? So I am updating my W by adding some point, right? So x times y, of course there is a label also which is 1 or minus 1. Nevertheless, I'm adding something to my old data point. So how much is my length of my WL plus 1 growing, right? So I can try to understand that quantity, right? So let's say I want to understand that quantity, and we'll see why that's a good quantity to understand. So we want to understand what is the length square, let's say, of WL plus 1. This is of course the length square of WL plus x times y square. But what is the length plus 1 of my old time? Observe where WL is in point and we are converged, right? So which is what we're going to tell them only makes an update when happens only when a mistake happens. Okay, so now let's say we are at some point in the running the perceptron algorithm. We are given some data set, we are running the perceptron algorithm, and let's say at some point WL, or maybe I'll put the L above, WL is the current guess, and a mistake happens. So with respect to some data point x comma y, right? So I found a point where WL is incorrectly classifying. So the moment I find a point where it incorrectly classifies, I'll update WL to WL plus 1 as WL plus x into y. This is my update rule. I know this, right? Now if you observe, what is happening is I'm adding a new point to my current old WL, right? So now what we're going to look at is we're going to ask how much is the length of my WL plus 1 growing, right? So I am updating my W by adding some point, right? So x times y, of course there is a label also which is 1 or minus 1. Nevertheless, I'm adding something to my old data point. So how much is my length of my WL plus 1 growing, right? So I can try to understand that quantity, right? So let's say I want to understand that quantity, and we'll see why that's a good quantity to understand. So we want to understand what is the length square, let's say, of WL plus 1. This is of course the length square of WL plus x times y square. But what is the length squared? This is the norm squared of a vector, which we know can be written as WL plus x into y transpose WL plus x into y, which is on expansion you will get 4 terms, which is WL norm squared plus 2 of the terms will be the same, which is 2 times WL transpose x into y plus x transpose x, which is norm x squared into y squared. This would be the expansion. Well, what is y squared? Well, y squared, y is plus or minus 1, so y squared is always plus 1. So this whole thing is going to be just norm x squared. But now how big can norm x squared be? Right? So x is any data point in my data set, and now I'm trying to understand what is the norm squared of x. But we made an assumption about the algorithm. I mean, one of the assumptions that we made before we started proving was the radius assumption, which said that the length of any data point is at most r. It's within a ball of radius r, which means the length squared of my data point is going to be less than or equal to r squared. So the third term is at most r squared because norm of x is less than or equal to r by our assumption. Now what about the second term? Well, it is 2 times WL transpose x into y. Now, what can we say about this term? Pause and think about this. This is a very interesting question to think about. What can you say about WL transpose x into y? Well, what happened with respect to WL for the point xy? Well, WL made a mistake for xy. Pause and think about this. This is a very interesting question to think about. What can you say about this term? Pause and think about this. This is a very interesting question to think about. What can you say about WL transpose x into y? Well, what happened with respect to WL for the point xy? Well, WL made a mistake for xy. That's why we are updating it to WL plus 1, right? So which means that WL is making a mistake for x comma y means what? Well, the sign of WL transpose x and the sign of y, which is plus 1 or minus 1, they don't match. Either WL transpose x is positive and y is minus 1, or WL transpose x is negative and y is plus 1. Which means if I multiply these two quantity, right? So then it necessarily has to be the case that because WL makes a mistake on xy, their product cannot be positive. The product has to be less than or equal to 0, right? So this guy has to be less than or equal to 0 because it has to be less than or equal to 0. So then we can say we can upper bound the whole thing by the norm of WL plus 1 squared by norm WL squared plus r squared. Because this is less than or equal to 0, I can throw away the term and just say that this is less than or equal to just the first term plus the third term, which we know is less than or equal to r squared. So now what is this telling us? This is telling us that I have a WL, I make a mistake, I change my WL to WL plus 1, and now this new WL plus 1's length squared can grow by at most the previous length squared plus r squared, right? So it cannot grow more than that. That's what this is saying, right? So it can grow at most by r squared. But now interestingly, well, how did I get WL in the first place? I got WL because there was some WL minus 1, and now I made a mistake with respect to some data point, and so I updated it to WL, which means the same argument should also apply to WL, right? So which means that I can say this is less than or equal to WL minus 1 plus r squared. This squared is at most WL minus 1's length squared plus r squared, right? So because WL came from WL minus 1 and its length grew by at most r squared. Now WL minus 1 came from WL minus 2, and then I can inductively keep going, and then I can say that this is less than or equal, which is less than or equal to WL plus 1's length squares. But W naught square is just 0 because our initialization of W naught was just 0, right? So this just tells us that, which implies what we are saying is that after you make LF mistake, right? So in some round you make some LF mistake, right? So this just tells us that, which implies what we are saying is that after your W that you end up is at most L times r square, right? So this is one observation 1, right? So we are saying the length cannot grow by too much. It can grow only by L times R square of WL, right? So of the W that we are maintaining. So now remember this L, makes an appearance here. That's the interesting part here. L is, remember, L is the number of mistakes that we have made so far, right? So we have made L different updates for our W, and so that is the number of mistakes that has happened, right? So this is mistakes. So somehow we are converting our length of W into a bound on the number of mistakes that we have. Of course, this is not enough to say the number of mistakes of a perceptron is bounded, because we are only bounding the length from one side. We need to bound it from the other side also, which is what we'll try and do next. Number of to a bound on the number of mistakes that we have. Of course, this is not enough to say the number of mistakes of a perceptron is bounded, because we are only bounding the length from one side. We need to bound it from the other side also, which is what we'll try and do next. We need to bound the number of mistakes of a perceptron is bounded, because we are only bounding the length from one side. We need to bound it from the other side also, which is what we'll try and do next. From the other side, to understand the same quantity from the other side, we want to use the fact that there is some W star which linearly separates our data set with gamma margin. That's the assumption on the data set that we have. We haven't used that assumption yet in this argument, right? So the way we are going to think of that is that I have WL plus 1, which is my new W after WL makes a mistake on X comma Y. And now I want to understand, how does this WL's dot product with the W star look like? Remember, W star is something that I don't know, because that's an assumption that I'm making about the underlying data set, that there is a W star which separates this data with gamma margin. I don't know what this W star is, but I know that there is some W star, so I can still reason about such W star. What I'm trying to reason about is, as my data set, as I make mistakes in perceptron, I keep changing my W, and I'm asking, how does my dot product with the W star change? We know that this is WL plus X times Y, because WL made a mistake on XY, transpose W star, which is just WL transpose W star plus W star transpose X into Y. Now, what can I say about W star transpose X into Y? Well, what is this quantity? Well, W star transpose X is the dot product that W star, the optimal W, makes with respect to my X, and then I'm multiplying it with a label. Now, what is the property of the optimal W? The optimal W, in fact, separates my data set with gamma margin, which means, by definition, W star transpose X into Y should be at least gamma, right? So this guy is greater than or equal to gamma, where gamma is some positive quantity. This is an assumption that we have already made, right? So that's the property of W star. So now, basically, what is this saying? This is then saying that WL plus 1 transpose W star is greater than or equal to WL transpose W star plus gamma. This is kind of telling us that, the previous dot product with the optimal W star has to grow by at least gamma once you make a mistake and update WL to WL plus 1, right? So WL plus 1's dot product with W star should be at least gamma more than WL's dot product with W star, right? So which means that I can do the same argument now for WL, because WL again came from WL minus 1, the growth of W star. So now, basically, what is this saying? This is then saying that WL plus 1 transpose W star is greater than or equal to WL transpose W star plus gamma. This is kind of telling us that, the previous dot product with the optimal W star has to grow by at least gamma once you make a mistake and update WL to WL plus 1, right? So WL plus 1's dot product with W star should be at least gamma more than WL's dot product with W star, right? So which means that I can do the same argument now for WL, because WL again came from WL minus 1, the previous mistake happened, and so I updated WL minus 1 to WL, and so that should have given me an extra gamma boost to my dot product with respect to WL minus 1, which means this is greater than or equal to WL minus 1 transpose W star plus gamma plus this gamma. This is this gamma. This guy is greater than or equal to this. Same argument, right? And now we can keep going and then say that WL plus 1 transpose W star is greater than or equal to W naught transpose W star plus L times gamma. But W naught, we know, is just the 0, all 0 vector, right? So this dot product with any W star is going to be 0, so this is just the 0, this quantity is 0, which means what we have is WL plus 1 transpose W star is greater than or equal to L times gamma. This is true. What it is saying is that as I make mistakes, my dot product with W star keeps increasing, right? So, and I know already from previous argument, as I make mistakes, my length of WL plus 1 cannot grow by too much. Somehow we need to relate these two things, right? So on one side we have an upper bound on the length squared of WL plus 1, on the other side we have a lower bound on the dot product with W star, right? So how can I combine these two things? Well, we can combine this if we can get a bound on the dot product with W star as a function of the length of WL itself. But that's not too hard to do, right? So for any X comma Y, let me put this in a different color. So this is right. So let's say we are here. Now, if you remember from our PCA discussion earlier, right? So if I take the projection of X onto this direction of Y, if this is a perpendicular vector, this makes a 90 degree in 2 dimensions. So now this point, which is like a proxy of X on the direction of Y, we know is just X transpose Y divided by norm of Y into Y, right? So this is some constant times Y, and the constant is just X transpose Y divided by Y transpose Y times Y in 2 dimensions. So now this point, which is like a proxy of X on the direction of Y, we know is just X transpose Y divided by norm of Y into Y, right? So this is some constant times Y, and the constant is just X transpose Y divided by Y transpose Y, norm Y squared, actually, norm Y squared. So now this point is this vector, right? So now we know by Pythagoras that this length is less than or equal to this length. Why? Because Pythagoras says that the length of the hypotenuse, length squared of the hypotenuse, is the sum of the length squares of the other two sides, right? So which means that this length squared, right? So the length squared of this guy, this length squared is less than or equal to the length squared of X itself. This is Pythagoras. Of course, Pythagoras would say that this is plus the length squared of this guy, but then we can ignore that and say that this is less than or equal to this. But what is this? If I unravel this, this is just X transpose Y is a constant squared, length Y squared divided by length Y squared squared, which is length Y power 4, is less than or equal to norm X squared, which implies that X transpose Y squared is less than or equal to norm X squared into norm Y squared. So basically, for any X and Y, what this is saying is that the dot product square is at most the length square times the length of X squared times length of Y squared, right? So this is, I mean, people might have seen this as a version of Cauchy-Schwarz inequality. So this is true for any X and Y, right? So, but now X and Y that we care about is WL plus 1 and W star, right? So we know already, right? So from 2, we know that L gamma, right, is less than or equal to WL plus 1 transpose W star. I've just written it the other way, right? So we know already, right? So from 2, we know that L gamma right is less than or equal to W, right? So we know already, right? So from 2, we know that L gamma, right, is less than or equal to WL plus 1 transpose W star. I've just written it the other way, right? So this is WL plus 1 transpose W star is greater than or equal to L gamma. Equivalently, L gamma is less than or equal to WL plus 1 transpose W star, which means that L squared gamma squared is less than or equal to WL plus 1 transpose W star squared. Now think of this as some x and think of this as y. Now this is x transpose y squared, which by Cauchy-Schwarz, our previous argument, has to be less than or WL plus 1 squared times W star squared, right? So this is from Cauchy-Schwarz. Now we use our assumption that we could have always picked my W star, which has a gamma margin such that W star's length is 1, right? So this length is just 1 without loss of generality. So I can forget that, and then this just then says that norm WL plus 1 squared is greater than or equal to this, right, L squared gamma squared. This is my third point, right? So on the one hand, we have from argument 1 that norm L plus 1 squared is less than or equal to L times R squared, whereas from the other side we have norm WL plus 1 squared is greater than or equal to L squared gamma squared, right? So which means that this guy is actually sandwiched between two terms, right? So this is greater than or equal to L squared gamma squared, this is from 3, and this is less than or equal to L R squared, this is from 1. Now this implies L squared gamma squared has to be at most L R squared, because this quantity is kind of sitting in between these two terms, right? So which means this has to happen, which now implies L is at most R squared by gamma squared. Now this means what, right? So this is kind of telling us what is L. L is the number of mistakes that we make in our algorithm, and now we are saying that this mistakes is bounded by a term which is R squared by gamma squared, where R is the radius assumption, the radius of our data, and gamma is the margin of the optimal separator, right? So this bound is what is called as the radius margin bound. So what is this telling us, right? So why do we care about this bound? This is telling us that the number of mistakes that perceptron makes is at most R squared by gamma square, where R is the radius of our data set and gamma is the margin with respect to the optimal W star, right? So this means that the number of mistakes is bounded because, well, why is this? Because gamma is positive, and so R squared by gamma square is a finite number. If gamma was 0, which means is bounded because, well, why is this? Because gamma is positive, and so R squared by gamma square is a finite number. If gamma was 0, which means that if we assume linear separability with 0, allowing gamma is 0, which means that we allow points to lie on the hyperplane that separates the pluses from the minuses, then we are saying this argument would just say that L is less than or equal to R squared by 0, which means L is less than or equal to infinity, which means the number of mistakes is less than or equal to infinity is a useless statement. But the moment we say that we don't allow gamma to be 0, that there is some W star such that gamma is strictly greater than 0, then we get a finite value as an upper bound, and so the number of mistakes that the algorithm makes is finite, and so the algorithm necessarily has to converge, right? So this implies perceptron converges. Summarize, what we are essentially saying is that we have an algorithm now which is based on a very simple update rule. When you find a mistake, just add x times y to your current W and keep going on. So this is the algorithm, and now this algorithm will run until convergence. But what does convergence mean? Convergence means that you run the algorithm until you find a W that correctly classifies all our data points. Now we are saying now that it will indeed converge because the number of mistakes that this algorithm can make is bounded by a function of the radius and the margin. And if radius is of course something that you can calculate from your data set, it's a finite number. And if you assume that the data set has a W star with a positive margin, then the number of mistakes is bounded, and so the algorithm necessarily cannot make more than a bounded number of mistakes, which means that eventually the algorithm has to converge, right? So if our data set satisfies linear separability with gamma margin, then perceptron converges in a finite number of steps. So this is good news because now we have an algorithm which is a super simple algorithm, and we know that it converges. It is useful to understand this radius margin bound and its implication carefully, and that is what we want to do next, because that will lead us to several other sophisticated algorithms a little later in this course. But the good news is perceptron converges. But then what does it mean to say with respect to the quality of solution that we get, and what does it mean to say that converges with mistakes less than or equal to R squared by gamma square, right? So what is the role of this gamma? How can we understand the role of this gamma more carefully, right? The role of the margin. So these are things that we need to think a little. The role of perceptron converges, but then what does it mean to say with respect to the quality of solution that we get, and what does it mean to say that converges with mistakes less than or equal to R squared by gamma square, right? So what is the role of this gamma? How can we understand the role of this gamma more carefully, right? So the role of the margin. So these are things that we need to think a little bit more carefully about this perceptron algorithm, and that will provide us more insights into developing new algorithms, which we'll see later in the course, right? So at this point, I would want to stop by saying that we have put down an algorithm which is a very solid algorithm, simple, solid algorithm, which has guaranteed convergence. In fact, this is one of the first algorithms in machine learning with provable convergence guarantees. And inspired by these algorithms, there are two major branches of thought which led to two different types of algorithmic development whose base was perceptron. We will see both of these in this course. One is called the neural network, and one is called the support vector machine, both of which have inspiration from perceptron and its analysis. And so this becomes a very, very interesting and important algorithm to understand in a classical machine learning setup. Okay, so with this we'll stop here, and then next time when we come again, we'll look at, you know, find linear classifier if the data that is given is linearly separable. We also argued that the perceptron algorithm's number of mistakes, right? So perceptron, the number of mistakes that perceptron makes depends on is at most, right? So let me put this way: perceptron mistakes is less than or equal to r squared by gamma squared, where r is the radius of the data points and gamma is what we were calling as margin. That is when data set is linearly separable with gamma margin, then what we are able to argue is that the perceptron's number of mistakes is a finite quantity. It's bounded by r squared by gamma squared. Now, this needs a very closer look. What does it mean to say the margin is gamma and so on? And that needs a longer discussion, and the algorithms that will come out of it will need a longer discussion. So what we're going to do is we're going to do this afresh in the coming week. But for now, we'll park the idea of perceptron that here is an algorithm, and we know that that algorithm converges when the data is linearly separable. That needs a longer discussion. Now, this needs a very closer look. What does it mean to say the margin is gamma and so on? And that needs a longer discussion, and the algorithms that will come out of it will need a longer discussion. So what we're going to do is we're going to do this afresh in the coming week. But for now, we'll park the idea of perceptron that here is an algorithm, and we know that that algorithm converges when the data is linearly separable, and we know the number of mistakes that it makes is bounded by the radius squared divided by the margin squared. This is the understanding that we have right now. We'll come back and revisit this idea of margin a little later, perhaps in the next week, where we will have a longer discussion about this and then see what kind of algorithms that this discussion will inspire. But for today, what we wanted to do is to see what is the assumption that perceptron makes, and can we rethink this assumption in a slightly different way. So if you remember, the assumption that perceptron makes is a linear separability assumption, right? So but if you want to write that in a probabilistic way, then one way to say that is that probability of y equals 1 given x. This value is just 1. That is, with certainty, you will predict 1 if w transpose x is greater than or equal to 0, and this probability is 0 otherwise, right? So that is, there is a probability, but then it is not really, a non-trivial probability, right? So which means that this is essentially, we have argued that this is essentially saying that the data set is linearly separable with the separator given by the plane perpendicular to w. Now, because of the strict assumption about these probabilities being just 1 or 0, perceptron is unable to model data sets like this, right? So if you have let's say plus minus 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 minus, let me put this in the black color. Now, if you have a minus here and if you have a plus here, we know that this data set is not allowed under the perceptron model. Why? Because when I'm trying to label this, when there is a labeler who's giving me labels for this data points, well, that is going to depend on some w, maybe the w is here, and that w says that, well, everybody on one side is plus and the other side is minus. But then if the labeler had used this w, then that labeler would have labeled this point as plus and this point as minus. But because we're seeing the other way in the data set, this data set could not have been generated according to the perceptron assumption, which is this. And if you look closely at this assumption, the main culprit is the fact that we are assuming that the probabilities are exactly 1 and 0. So can we somehow relax this assumption, right? So that's the question we're going to ask now, and then we'll see that what kind of algorithms that will lead us to. So the question we're going to ask is, can we model the probabilities differently? Want to do this, right? So we can start with a simple model, right? So start with a simple model. Well, what is a simple model? A simple linear model. Simple models are typically linear. What does that mean? That means that you have some z, so which is like a score for a data point with respect to the model, assuming could not have been generated according to the perceptron assumption, which is this. And if you look closely at this assumption, the main culprit is the fact that we are assuming that the probabilities are exactly 1 and 0. So can we somehow relax this assumption, right? So that's the question we're going to ask now, and then we'll see that what kind of algorithms that will lead us to. So the question we're going to ask is, can we model the probabilities differently? What do I mean by differently? Well, let's see what does differently mean. There are several ways you can model it, and here is one natural way that you might want to do this, right? So we can start with a simple model, right? So start with a simple model. Well, what is a simple model? A simple linear model. Simple models are typically linear. What does that mean? That means that you have some z, so which is like a score for a data to some w, right? So x is again your feature, right? So this is your feature vector. X is in RD as usual, and then there is some w data. There are several ways you can model it, and here is one natural way that you might want to do this, right? So we can start with a simple model, right? So start with a simple model. Well, what is a simple model? A simple linear model. Simple models are typically linear. What does that mean? That means that you have some z, so which is like a score for a data point with respect to some w, right? So x is again your feature, right? So this is your feature vector. X is in RD as usual, and then there is some w. But now if I do w transpose x, and if I'm looking at that value, now that value is like a score that w gives for this data point x, right? So in pictures, it would mean something like this. You have this two-dimensional plane. Let's say this is our usual w that we typically take as an example. Now this line is just a set of all x such that W transpose x equals 0. That is the score that W gives to all the x on this line is just 0. Now, one might ask where are the set of points for which the score is 1, right? So now if you think about that, so that's going to be somewhere here, right? So that's just going to be a line which is parallel 1 unit with respect to W. So this is just the set of all x such that W transpose x equals 1. Now similarly, where are the set of points for which the score is -1? Remember, the score is just a dot product the way we are thinking of it. So the score could be -1 and that -1 could be somewhere here, right? So this is set of all x such that W transpose x equal to -1. Well, if it is the score is negative, then we are somehow saying that the data point is highly probable to be labeled -1. If the score is positive, then the data point is probable to be labeled as positive. But now there is a difference that we want to incorporate in our model between data points that are here and perhaps a data point which is maybe somewhere here, right? So maybe this is a line which also has a data point. Now this data point, is the set of all x such that let's say W transpose x is 100. Right, so if you move 100 units away in the parallel in the direction of the plane that separates, that is perpendicular to W. Now if I'm generating these two, if I'm generating labels for these 2 points, let's say somebody gave me these labels, and now I have to give you, let's say somebody gave me these points, right? So let's call this x1 and let this point as x2, and now I have to give you labels for these points. Well, I want to somehow associate a probability with these labels, right? So this label can be either 1 or -1. Earlier we were saying that this probability that the label is 1 if it falls on one side of W, which means that both these points will get labeled as 1 with probability 1 for this W, right? So whereas there might be 2 other points on this side, maybe x3 and x4, maybe x3 is here, and there is a corresponding, maybe there is some x4 out here, which I'm going to put it here. So this is the set of all x such that W transpose x equal to -150, let's say, right? So this is parallel on this side, 150 units. So now I have to label x1, x2, x3, and x4, right? So I have to give you labels. Earlier, our assumption would say that I will just give you labels 1 for x1 and x2 and -1 for x3 and x4, and that allowed only linearly separable data sets. Now what I'm going to say now is that I'm going to allow for labels to be both +1 and -1 for all points. But what will decide these labels? Well, there should be some probability for the label being +1 and there is some probability for the label being -1 for each of these points. Now what will decide this probability? That probability will be decided by how high or low the score associated with this point is, which means that if I take a point like x1 which is here versus x2 which is here, now if you ask the question, well, which one should get a higher probability of being assigned to +1? Well, for this W, this x2 is much far away from the separator, right? So which means that you are somehow more confident that this point has to be labeled +1 as opposed to x1 which is close to the boundary, which means that the probability that it should be labeled +1 should be lesser than the probability that x2 is labeled +1, right? So which means that as I move in this direction, my probability that the point is labeled 1 should increase, whereas as I move in this direction, the probability that a point labeled -1 should increase, right? So still remember, every point gets a non-zero probability of being +1 or -1, but then the chance that it becomes -1 somewhere here on the end of if you move further away in this direction goes down, right? So somehow we need to capture this intuition using the score, right? So but remember, the score itself is not a probability, right? So the score z is in -infinity to infinity, right? So it's a real number. So we have to convert the score somehow into a probability, and the question is how can we do that, right? So what do we want here? We want the following: large, which means that as I move in this direction, my probability that the point is labeled 1 should increase, whereas as I move in this direction, the probability that a point labeled -1 should increase, right? So still remember, every point gets a non-zero probability of being +1 or -1, but then the chance that it becomes -1 somewhere here on the end of if you move further away in this direction goes down, right? So somehow we need to capture this intuition using the score, right? So but remember, the score itself is not a probability, right? So the score z is in -infinity to infinity, right? So it's a real number. So we have to convert the score somehow into a probability, and the question is how can we do that, right? So what do we want here? We want the following: larger the value of z, larger the score, which is z W transpose x, more the probability minus probability. Well, what we want about the score, right? The first question is what happens if we find a point which lies on the separator, right? So it's exactly lying on the separator, which means that we are not really sure if there's going to be +1 or -1, so we can give equal probabilities for them, right? So which means that we want some function g such that which takes the score as input and outputs as probability, but this g of z should be 0.5 if z equals 0, right? So whenever the score is 0, which means that the point lies exactly on the separator, we want the probability of that being labeled +1 as 0.5 and -1 also as 0.5, equal probability. Now we want g of z, the probability of the point being labeled 1 to converge to 1 as z becomes larger and larger, which means that as z becomes infinity. Similarly, we want g of z to converge to 0 as z becomes -infinity. The smaller and smaller the score is, the chance that it being labeled as +1 should go to closer and closer to 0. So any g that satisfies these 3 properties is a reasonable g to use, right? So this g is sometimes in literature is called as a link function. Popular link function is one popular choice for the score is, the chance that it being labeled as +1 should go to closer and closer to 0. So any g that satisfies these 3 properties is a reasonable g to use, right? So this g is sometimes in literature is called as a link function because it links scores to real numbers to probabilities. There are several link functions that you might encounter in practice, but one of the most popular link functions, one popular choice for link function is the following. So g of z equals 1 divided by 1 plus e to the minus z, right? So this function is called sometimes as the sigmoid function or logistic function, and I'll plot this function and show you how this looks like, right? So this function will take a negative value, as you can see, right? So it's or logistic function, and I'll plot this function and show you how this looks like, right? So this function will look like the following. As you can see, right, so it's e power something, so it's always going to be positive, and it's 1 divided by 1 plus e power something will always be a positive quantity, right? So it will take a value of 0.5 when z is 0. So this is z, this is g of z equals 1 by 1 plus e power minus z, and here is 1, and let us put a larger and larger, right? So this is 0, this is infinity, this is minus infinity. As z grows larger and larger, the sigmoid function's probability that it gives that z the point is labeled +1 goes closer and closer to 1, and as z becomes closer and closer to minus infinity, the probability becomes closer and closer to 0. It's called a sigmoid because this looks like an s, and s stands for sum, and sigma is the the Greek symbol for sum, and so it's called a sigmoid function. Okay, so this is a reasonable choice, and we'll see why this is a reasonable choice later on, because it makes certain math easier, as we will see in a minute. But now this is all we are saying right now is that we have a model as to how the data could have been labeled. Now let's ask the question, well, can I, under this model, do I allow a data set like this, right? So this is what we were not allowing earlier, right? So So if the moment I put a minus and plus on the opposite side of the one fixed W, then it's not okay. Now, is this data set allowed according to this model, right? So this model is sometimes called the sigmoid model or the logistic model. Do we allow this data set? Yes, we allow this data set because now there might be some W, right? So such that so these points, so for every point in my data set, before deciding the label, this is what should have happened, right? So for example, let's take this point. Why was this label +1? Why is this label positive? Because this point falls with respect to this W on this line, and this line is just the set of all x such that let's say W transpose x is 1, which means that I have actually tossed a coin whose probability of coming up heads is 1 by 1 plus e power minus 1, which is 1 by 1 plus 1 over e, which is e by e plus 1, right? So this is the chance with which this point gets labeled as +1. So which means that I've tossed a coin, and the coin whose biased, right? So probability of falling heads is e by e plus 1, and the coin actually fell heads, and so this point was labeled as +1. That's the assumption we make. Now, why was this point labeled -1? Well, now again you do the same process, right? So this point is in the set of all x such that W transpose x equal to maybe 10. Now in this case, well, again there is a chance that this guy gets a positive label, and that chance is in fact greater than the chance that this guy gets a positive label. In fact, that will be 1 by 1 plus e power minus 10, right? So it should be e power 10 by e power 10 plus 1. Right, so now I have tossed a coin with this probability, and that coin fell tails, right? So I have labeled this point as -1. It is not a 0 probability that it will show up as -1, right? So though it's a minuscule probability, in that if you do an experiment where you're assuming that the labels were generated according to this coin tosses, where the coin's bias depends on how far away from the separator this point is, in the sense of the score that we have defined earlier. So then every point could get some chance of being +1 or -1, right? So now we're assuming that these points have been labeled because they fell heads or tails according to their labels, right? Now what might ask the question, well, the moment I say that, well, every point could have been +1 or -1 depending on how far away it is from the separator that defines W. Now one can say that, well, why only this W, right? So I could have had a completely different W. Maybe I'm looking at a different W here, right? So now this is W dash. This W dash separates like this. Now I can still say, right? So even with this W dash, this data set is still possible. Why? Because this data set, now the same point here now would have a different line, right? So a different score with respect to this new W that I've defined here, right? So I mean, I should draw the W carefully so that it looks perpendicular, but yeah. Right, so this with respect to this W, again I get a probability that each point is +1 or -1, so I would have tossed a coin and I've gotten this labels, right? So basically then that means that you have seen a data set with certain labels. Now every W has a probability of generating these labels, right? So now every W could be is a contender for being the W that actually generated the labels, which means then now our problem becomes as to because every W is a possible W, I need to pick one W which I think would be the best W for this data set. So now I can pose this as a problem where I'm trying to find that W which has the highest chance of having generated this data, which is simply a maximum likelihood estimation problem, because for every W there is a probability that it generates the data that I see, the labels that I see. So which W has the highest probability of generating this data? That's a typical estimation problem that we know how to solve, right? So let's go ahead and do that.